Today we will be discussing matrix of a relation. What we will see that given a relation from a set A to B or a relation on a set A, we can define a binary matrix corresponding to the relation, and this matrix plays an important role in studying properties of relations and operating one relation by another relation and so on. So, to begin with, let us start with a set A given by A1 up to An and a set B given by B1 up to Bm. Now, suppose R is a relation from A to B, and of course, n and m are finite positive integers. What we can do is that we can label the rows and columns of a matrix by the elements of A and B respectively. For example, let us write A1, A2, A3 one below another, and B1, B2, B3 and so on up to Bm. And now, we have positions of matrices indexed by A1 B1, A2 B2, A1 B2, A1 B3, A1 Bm and so on. We can fill in these gaps by writing M11, M12, M13 and M1m. In the next row, we write M21, M22, M23 and so on M2m. At this point, let us just change the notation a little bit and understand that this m and this m are not same. So, probably write this as m dash. So, we have got B1 up to Bm dash, this is 1 m dash, 2 m dash and so on. The next row we have M31, M32, M33 so on up to M3 m dash, and then M n1, M n2, n3 so on up to M n m dash. Now, as we have already studied that a relation is nothing but a subset of the Cartesian product of A and B. Therefore, what we will do is that if a pair A I B j belongs to the relation, we will put 1 in the corresponding M I j, and if it does not belong to the relation, then we will put 0. So, we will write M I j equal to 0 if A I B j is not in R, and we will write M I j equal to 1 if A I B j belongs to R. And if by using this rule we fill in the matrix that we have already written down, the Mij matrix, then we will find that it becomes a binary matrix. So, what we will write is that this matrix that we denote by M sub r is equal to M 1 1 up to M 1 M dash, M 2 1 up to M 2 M dash, and so on, and at the in the last column it is M n 1 up to M n M dash. Now, of course, here we will assume that we know the ordering. The ordering is fixed. The ordering of the set A, in which we have labeled the, by using which we have labeled the rows of the matrices, rows of the matrix, and the ordering of the set B, by using which we have labeled the columns of the matrix M sub r. It is now clear that the matrix M sub r is a binary matrix. There is a special case of this which is used very often, that is when A and B are same. So, in this case we have only one set A which is finite, consisting of elements A 1 up to A n, and we have a relation R, well, which is a subset of A cross A. So, this relation is a relation on A, and then we write M sub r, which is the matrix corresponding to the relation R, which is given by M I j, which is an n by n matrix defined by M I j is equal to 0 if A I A j is not in R, and 1 if A I A j is in R. We will now look at some examples related to this idea of a matrix of a relation. So, first of all we check a well known example, that is the relation less than or equal to on the set 0, 1, 2, 3, 4. So, in this case the set A is the set 0, 1, 2, 3, 4. We may even write that here. Now, we are to construct the matrix corresponding to the relation given by less than or equal to. Let us call that matrix M sub less than or equal to, which is equal to, now at this point we have to label the rows and columns. Let us do that. We label the columns by 0, 1, 2, 3, 4 and label the rows by 0, 1, 2, 3 and 4. Of course, we have a matrix over here and there are entries that we have to fill in. So, let us start constructing the matrix. We take 0 and 0 from here and here and we ask the question, is 0 less than or equal to 0? The answer is yes, therefore, we write 1. After that, we ask the question, is 0 less than or equal to 1? The answer is yes, therefore, we write 1. Then we ask the question, is 0 less than or equal to 2? The answer is yes, and therefore, we write 1 over here. And like this, we fill in 1s in all the entries of the first row, because 0 is less than all the elements of the set 0, 1, 2, 3, 4. Then we move to the second row and we start checking. We ask the question whether 0 is, whether 1 is less than or equal to 0, which is not true. Therefore, we write 0 over here and then we write whether, then we ask whether 1 is less than or equal to 1, and of course, we know that 1 is less than or equal to 1. Therefore, we get 1 over here, 1 is less than or equal to 2. So, we get 2 over here, 1 over here, and similarly this. In the third row, the first column entry is 0, because 2 is not less than or equal to 0, 2 is not less than or equal to 1. So, 0 over here and then again 1. In the similar way, we can fill in all the entries of the matrix and we get a matrix as this one, right. We will now look at another example where we are given a digraph and we are asked to find out the corresponding matrix. Well, that means that essentially a digraph is connected to a relation is connected to a binary matrix. Therefore, in effect any digraph is related to a binary matrix, and if somebody looks at graph theory by not looking at relations, then of course, there is a graphs are related to binary matrices, and those matrices are called adjacency matrices. So, what we are looking at as matrices of relations are in a sense equivalent to adjacency matrices of digraphs. And let us look at this example. Now, we have 5 vertices V1, then V2, then we have V3, and then we have V4 and we have V5, and we have an edge joining V1 to V2 and V2 to V3, and then we have an edge joining V3 to V5 and an edge joining V4 to V1 and V4 to V2, right, and there is a edge joining V3 to V4. So, we draw a line from V3 to V4 and put an arrowhead towards V4. So, this is the graph that we have got. So, the underlying set of vertices or the set on which the relation is defined is V1, V2, V3, V4 and V5, and we would like to know the relation let us suppose the relation given by the digraph be denoted by R. Suppose R is the relation given by the above digraph, all right, and we would like to find out MR. For that, we again label the rows and columns of a matrix by the elements of A according to the order given here. We could have basically chosen any order, but we have to specify the order at some place, possibly at the beginning. So, let us now write V 1 up to V 5 and V 1 up to V 5 as the labels of the rows, and then let us start checking here. See, V 1 is related to V 2, therefore, I put a 1 here, and V 1 is not related to anything else, therefore, I am free to put 0 in all the other places. Now, let us look at V 2. V 2 is related to V 3, well, I put a 1 there, and otherwise V 2 is not related to anything else. Therefore, I will put zeros as the other entries of the second row, and then we come to V 3, that is the third row, and in the third row V 3 is related to two elements V 4 and V 5. So, V 3 is not related to V 1, so I put a 0 over here. V 3 is not related to V 2, I put a 0 over here. V 3 is well, V 3 is not related to itself, so I put a 0 here, but V 3 is related to V 4, therefore, I will put a 1 over here, and V 3 is related to V 5, so I put a 1 over here again. And then we go to V 4, where we find that V 4 is related to V 1, therefore, I put a 1 over here, and also it is related to V 2, I put a 1 over here, and rest of the places I put zeros, and V 5 is not related to any other element. Therefore, I put all zeros in the fifth row. Thus, we have the basic matrix corresponding to the relation R, and we can write, if we choose to forget the ordering, that is to say, suppose we fix the ordering once and we say that okay, fine, we do not write the ordering beside the rows and columns of the matrix all the time. Therefore, we can write MR as 0 1 0 0 0, 0 0 1 0 0, 0 0 0 1 1, and 1 1 0 0 0. And at the end we have another row, that is all 0 row, that is corresponding to V 5. So, this is the matrix corresponding to R. Now, we move on to see what we can do with these matrices. Sometimes these matrices are useful in computing the results of operations on relations. For example, we have seen before that given several relations on a set, we can take union, intersection, and composition of those relations. And sometimes what happens is that if we are able to construct the corresponding matrices, then we can determine the union, intersection, composition of several relations very quickly and possibly by using a computer. Therefore, let us see how to deal with unions. For that, we have to just see some general definitions. So, suppose R and S are two relations on a set A. Suppose R and S are two relations on a set A of cardinality n finite, all right, whose matrices are given by MR, well, which is, I will write it as Mij, this is so it is n this is n cross n, and we have MS which we denote by, let us say, m dash I j n cross n. Then we know that all these m I j's and m dash I j's are elements of the set 0 1, and on the set 0 1 we have the usual operations or and given by this operation is known as OR and this operation is known as AND. We use these elementary operations to define operations on the matrices of relations. We will define MR or MS as Mij or m dash Ij n cross n. That is, we take these two matrices and then we take element wise OR to get another matrix which we call OR of these two matrices. Similarly, we will take these two matrices MR and MS and take element wise AND to determine another matrix which we will call the AND of these two matrices. Now, the question is that what is the use of doing this? We will shortly see that and OR of these two the AND OR of these two matrices correspond to union and intersection of the relations. Let us look at it by an example. So, we check one example. We consider a set A which is 1, 2, 3 and 4, and then we will consider a relation on A given by 1 2, 1 3 and 2 4. We consider another relation S on A given by 1 2, 2 3 and 4 4. All right. Now, let us look quickly at what is R union S. R union S is given by 1 2, 1 3, 2 3, 2 4 and 4 4, and R intersection S is the singleton given by 1 2. Now, let us see what happens if we consider the matrices instead of these sets. M r is equal to, now let us label the rows 1 2 3 and 4, 1 2 3 and 4. So, 1 is related to 2, therefore, I put a 1 over here, and 1 is related to 3. So, I put a 1 over here. So, it is 0 and this is 0, and 2 is related to 4, and that is all, and there is no pair inside R, therefore, I complete the matrix in this way. All right. So, I write it again. So, the matrix corresponding to M r is 0 1 1 0, 0 0 0 1, 0 0 0 0 and 0 0 0 0. Now, let us find out the matrix corresponding to M s. Again I have to label first 1 2 3 4 and 1 2 3 4, and if I write like this, then in M s 1 is related to 2. So, I will put a 1 over here, and 2 is related to 3. So, I will put a 1 over here, and then I have 4 is related to 4. So, I put a 1 over here, rest of the entries are zeros. So, I will get something like this, and 3 is not related to anything, therefore, I will put all zeros over here. All right. So, I have got this one. Now, I would like to take M r or M s. For that, I process these two matrices. Now, I check the first entry in M r and M s both are zeros. So, 0, second entry both 1. So, 1, third entry 1 0, 1 0 is 1, therefore, it is 1, and 0 0 is 0. So, therefore, it is 0. Then in the second row we have 0 0, 0 0, 0 1. So, therefore, we have got 1 over here and then 1 0. So, we have got 1 over here, and similarly, if we check the third row, we will find that this is all zeros, and then at the end in the fourth row, please see that if we compare the elements of MR and MS, then first 3 entries are zeros in both the matrices, therefore, the result is 0. Only in the last one in MS, the 4 entry is 1. So, therefore, I will put a 1 over here and rest of the cases it is 0. Now, let us try to construct the relation corresponding to this matrix. We see that in this relation we will have this is 1 is related to 2, and then the entry 1 3 is 1, therefore, 1 is related to 3. Then in the second row 2 3 is related to 3, and in the again in the second row 2 4 is related to 2 is related to 4, and then at the end 4 is related to 4. So, we see that the relation corresponding to the matrix MR or MS is 1 2 1 3 2 3 2 4 and 4 4, which is exactly same as the relation R union S. So, the matrix that we have obtained is nothing but the matrix corresponding to R union S, and this is in general true. Therefore, we have one result which says that MR or MS gives me the matrix corresponding to M R union S. Now, what about the intersection? Let us look at the same pair of matrices. So, we have again MR, which is equal to 0 1 1 0 0 0 0 1, then 0 0 0 0 and 0 0 0 0, and we write MS, which is 0 1 0 0 0 0 1 0, and then the third row is totally 0 and the last row is all 0 except at the last entry where we have 1. And now, we check AND of these two relations MR and MS, which gives me, well, I can compare in the same way. I can see that the first entry of MR and first entry of MS is 0. So, I put a 0 over here. The first row second column entry is 1 in both the matrices. So, I put 1 over here and the rest 2 are zeros. Please note here that in the previous example we were using element wise OR. So, we 0 or 0 is 0, 0 or 1 equal to 1 or 0 equal to 1 or 1, which is equal to 1. But in this case the element wise operation is AND, therefore, it is basically making most of the things 0. So, I have got 0 0 is 0, 0 1 is 0, 1 0 is 0 and 1 1 is 1, and that is the rule that I am using. So, we see that if we look at the second row and element wise, I see that there is no common 1 as entries. Therefore, all the entries will be zeros, and of course, the third row is 0 in the first and also in the second matrix, therefore, all 0, and the fourth row is 0 in the first matrix, therefore, it is 0. Therefore, we have a singleton, and that is this singleton is the entry first row second column. So, it is 1 2. Therefore, the matrix the relation corresponding to the matrix MR, well, here is a mistake, this is and. So, let me write it down. Well, here this is and. So, MR and MS is equal to 1 2 and which is R intersection S. Therefore, we can write MR and MS is equal to M R intersection S. Next, we will look at the scenario of what happens if we take a product of two matrices corresponding to two relations. The question is that whether it connects to some basic operations on relations. So, let us look at what happens if we just take matrix product. So, again we are considering a set A which consists of n elements, and we have a matrix R, matrix of R defined as M R, which is essentially M I j. It is an n cross n matrix. We have another matrix M S, which is, let us say, is given by S I j, which is n cross n. And now, if I just take a product of these two matrices, usual matrix product, then we will get M R M S, which is equal to some T I j n cross n, where T I j is equal to sigma k going from 1 to n M I k S k j. Of course, this is usual matrix multiplication, and well, we have to remember that in this case the summation that we see in the right hand side of the equation containing T I j is a summation over integers. Now, we ask a question that what happens if T I j is 0 for a pair I j. So, that means if T I j equal to 0, then there exists no k belonging to 1 to up to n such that M I k S k j is not 0. So, that means that In other words, there exists no a k belonging to A, right, such that A I related to A k and A k related to A k related by S well A k related to A j. We have to remember here that this relation is S and this relation is R. So, there is no A k such that this holds, but that means that this implies that A I is not related by R composition S to A j, or if we want to be a bit more specific, then we will write A j A I A j does not belong to R composition S. Now, suppose we have a situation where the sum T I j is not equal to 0. Suppose T I j is not equal to 0, then please note that this summation is a sum of non-negative integers, because m I k and s k j are non-negative integers. Therefore, if T I j is not 0, there has to exist at least one k such that well m I k equal to s k j equal to 1. So, let me write that. Then there exists k belonging to 1 up to n such that m I k s k j both are 1s. That means that is A I related by the relation R to A k and A k is related by the relation S to A j, which implies A I R composition S A j, or if we like to write A I comma A j, the ordered pair A I A j belongs to R composition S. Thus, this proves that M R product M s has something to do with the matrix corresponding to the composition of R and S. What we do is that we slightly modify the definition of product and we write M R, then a small dot and then M s. We write this, that this is equal to, let us say, T, just put a small dash over it, I j, where T I j dash is 1 if T I j as we have defined above is not equal to 0, T I j dash is 0 if T I j equal to 0. So, we define a new matrix M R composition M S in this way, and it is clear from the discussion that we had that this is same as the matrix corresponding to M R composition S. Let us look at an example of this this composition rule. So, let us again go back to the matrices that we were talking about here. As you can see that this M R is this and M S is this matrix. We will write afresh these matrices and take the product M R product M S, which is equal to 0 1 1 0 0 0 0 1, then 0 0 0 0, then 0 0 0 0, and here we have this new operation on matrices, and then 0 1 0 0 0 0 1 0 0 0 0 0 0 0 0 1. Now, we start checking the elements. If we see that the first row first column is 0, second row first row second column also 0, but then if we go to the first row third column, then we get a 1 and then 0, and then if we check the other entries, we will see that they are 0 0 0 1 and rest are zeros. So, either one can compute this directly, or one can take a product, the usual product of these two binary matrices, such that the elements are calculated over, the sum is calculated over integers, and then then modify the product matrix by the rule that if the entry is 0, it is 0, that if the entry is non-zero, put 1, then you will get this matrix, and this is the matrix corresponding to M R composition S. That can be directly checked. We have done this example in one of our previous lectures. So, therefore, we have R composition S is given by 1 3 and 2 4. In this lecture, we have defined relation the matrix corresponding to a relation, and we have basically seen that this matrix is nothing but adjacency matrix of a digraph, that is the digraph corresponding to the relation. So, we have a situation like this, we have digraphs, then we have matrices, let us say binary matrices, and we have relations. And what we have done is that we have developed connections among all these different concepts. We have seen that essentially they are same, and then we have seen that the basic operations and compositions of relations can be expressed very nicely as operations over binary matrices. This is what we do in this lecture. So, thank you.